Alright, class. Today we are going to talk about titration, which is a process to find the unknown concentration of an acid by using the known concentration of a base, um, and vice versa. So, meaning you can figure out the unknown concentration of a base by using the known concentration of an acid. Um, the setup of this process look like this, where we have a burette and we have an Erlenmeyer flux. In the burette, we usually put the standard solution, meaning something that we know, the concentration of the standard solution must be known, and then we can figure out the volume of the standard solution by using the reading from the burette, right? So we have a starting point and then we have an end point, and the difference is going to be the volume of the standard concentration, right? So it could be acid, could be base, depending on our unknown. So in the Erlenmeyer flux right here, we usually have our unknown, and that's the concentration we're trying to figure out. And the volume should be known because you can use a graduated cylinder to measure the volume of the unknown concentration, right? So the volume of the unknown concentration should be known because we have different equipment to figure it out. Now, that's the process. So if we wanted to figure out any unknown concentration of an acid or a base, we can do titration to figure it out. And that's the whole process that we are going to talk about. So I hope you have your reference table in front of you, because if you go to reference table T, there is a formula for titration given to you. And the formula is MAVA equals MBVB, where M stands for molarity, the concentration, and A or B stands for acid or base. V, on the other hand, capital V, stands for the volume, right? So MA meaning concentration of the acid times VA meaning volume of the acid equals Mb times Vb, meaning concentration of the base times the volume of the base. They're equal to each other because at the end, after the titration, everything should be neutralized, meaning all acids and bases are going to produce salt and water, which is something that is neutral. For an acid-base titration process, we often use indicators. For example, let's assume that we have an unknown concentration of an acid, which we would like to figure it out, right? And the volume of the acid is, let's just say, 50. So assume that we have hydrochloric acid. We don't know the concentration, so it could be 2 molars, could be 5 molars, could be 10 molars. And the volume, which is known in this case, it would be 50 milliliters, right? So to figure out the concentration of that acid, we have to use a base, which has to be known, meaning standard base. And the standard base, we can use it in the burette. And the concentration of that base, it's standard, meaning you have to know this, and assume that it's 2. And the volume of the base, we can figure it out by reading the starting and the end point from our burette. So this burette started at 10. Here it's started at 0. Over here it's 10. Then we have 20. Then we have 30, 40, and 50, right? So we can read the marks from the burette to figure out how much we used, and then that would be the volume of the base. So the volume of the base, it's a matter of time before we figure it out. So for an acid-base reaction, you are going to use base to neutralize the acids for this process, right? But how are we supposed to know that we neutralize all the acids, right? So you can use a pH meter, which would give you an accurate reading, but most of the time what we do in lab is use an indicator. So we have, in this case, we're going to use an indicator. And what is the job of an indicator? Indicator will indicate, right? So depending on what kind of indicator you are using, it will indicate a color, and sometimes it's colorless, right? It doesn't indicate anything, but it gives you an idea of a pH. So if you look at reference table M, you have a bunch of indicators given in reference table M, and one of the indicator that is commonly used is phenolphthalein, right? Which is colorless. So phenolphthalein is colorless in an acidic solution, meaning any solution that has a pH 8 or below, right? Usually acidic solutions have pH below 7, but phenolphthalein is going to be colorless if the solution has a pH 8 or below, lower, right? But phenolphthalein is going to have a pink color if the solution has a pH of 9 or above, right? So that's the indicator we can use, or we usually use for an acid-base titration, because it changes the color from being colorless, it goes to pink. So when we start with an acidic solution, the solution, we're not going to see any color, but eventually when the solution is neutralized, we're going to see a very, uh, faded pink color. So usually it would look like. So at the starting point, you will have no color whatsoever if you're using phenolphthalein indicator, because it's an acidic solution, and phenolphthalein is colorless in an acidic solution, right? So it's colorless in an acidic solution if you're looking at this part right here. But as you are adding bases to that acidic solution, right? So let's just say you're adding bases drop by dropwise. That drop is going to right here change the color to pink. But it's not going to be stable because your solution is still acidic, even though that drop was a basic, right, solution. So right away you will see the pink color, but it will be gone because the solution is still acidic. When the solution is neutral, that's when the color will be changed to very, very light pink. Usually we call it endpoint. Endpoint is where we see a color change, right? So if we, that's why majority of the people use phenolphthalein, because it goes from colorless to pink. So when you see the pink color, which is stable, that's when you know that all acids has been neutralized. And then if you continue to add more, uh, you know, bases, then obviously it will go way too much, right? It will go way too far, and now the solution is going to be completely pink for phenolphthalein, because now your solution is no longer acidic or neutral. Instead, it is a basic solution. So this is what we need to be very careful during a lab experiment. We want to have see the pink color, but something that is not, dark pink. So what is an equivalence point, right? Like, what does endpoint means? What are those terms that we are using? Equivalence point is where the acid has been completely neutralized, meaning it might be even before we reach the endpoint, right? So equivalence point is when you are, let's just say, using hydrochloric acid versus sodium hydroxide base. Equivalence point oops, is where we have those HCl and sodium hydroxide, all of them reacted to produce salt and water. So in this case, we're going to have NaCl plus H2O. So equivalence point is where the acid has been completely neutralized. It is usually signaled by the endpoint, where an indicator causes a sharp change in the color of the solution. So if you look at this, we had nothing over here. We have something, slightly something over here, and then suddenly we have a solution that is pink. So that's the sharp change, right? That's the endpoint, meaning we should stop work, and we need to realize that all the acids or bases are completely neutralized. So in acid-base titration, indicators are substances that have distinctly different colors in acidic and basic solution. One commonly used indicator is phenolphthalein, which is colorless in acidic and neutral solutions but reddish pink in basic solutions. At the equivalence point, all the hydrochloric acid present has been neutralized by the added sodium hydroxide base, and the solution is still colorless. However, if we add just one more drop of sodium hydroxide solution from the burette, the solution will be basic and will immediately turn pink. So even though it's an acid-base solution, um, we are considering the color change as an endpoint, but in real life, we still need to understand that especially for phenolphthalein, when we see the color pink, it's actually more closer to the basic solution, right? Because the pH is, if we go to reference table, uh, table M, we can see that anything that is 8 or lower, phenolphthalein would be colorless. So even though we reach the neutral pH range, which is 7, phenolphthalein is still going to be colorless, right? Anything slightly above 8, it will start, getting to the color of pink. So this is something we need to be very careful when we are talking about titration process during a lab. Now, uh, another way to identify the neutralization point is by using a pH meter, right? So that's far more accurate than just using an indicator. In this case, titration curve, which is pH, which shows pH as a function of volume titrant added of a strong acid-base titration. So we can, in this case, we have 0.1 molar of sodium hydroxide solution. The titrant is added from a burette to 25 milliliter of a zero point 0.1 molars HCl solution in an Erlenmeyer flask. And if we started with an acidic solution, you can see that the pH range is much lower, right? Which is around 1. In this case, it's exactly 1. And as we're adding bases, uh, drops of basic solution, right? The pH is going up, which should make sense. So you started with completely acidic solution, and as you're adding bases, right, the pH will go up because now you have more hydroxide in that solution. So when the solution is completely neutralized, then your pH level is going to be 7, but that's when we reach the equivalence point. But let's just say the solution was not pink, right? It was still colorless. We're still going to add more bases because to see the endpoint, right, for phenolphthalein. However, when we add more NaOH, sodium hydroxide, to our solution because it was still colorless, eventually the pH will go up, right? And now we are going to have a solution that will basic, and this is when phenolphthalein is going to be completely pink instead of being colorless. So this is an image of when you do a pH when you do an acid-base reaction in a lab, this is what you might see. You will start with an acidic solution in an Erlenmeyer flux, which is colorless for phenolphthalein indicator. But then again, as you add base through the burette, right? If you're adding base through the burette, the solution will start turning to pink, right? Um, phenolphthalein is pink for a basic solution. So this is the pink color we might get during lab. And again, the goal is to get like um, very, very, very light pink uh, to go like to see our endpoint and to be precise with our equivalence point. But during lab, we make usually we make mistakes, and that's when we might get dark pink. And that's why it's always a good idea to have like bunch of trials to figure out the exact endpoint or equivalence point in this case. So in our next video lesson, we're going to learn how to use the acid-base formula to figure out the unknown concentration of an acid or base by using a standard or known concentration of the other one. So this formula is going to help us to figure out why we do those process in a lab or in a chemistry lab, right? So let's go through this briefly and then we can talk more about it in our next video. So suppose we have a an unknown concentration of an acid, hydrochloric acid. We know the name, but we don't know the concentration. So don't get confused. You might know that it's a hydrochloric acid, but you might not know how strong it is, right? So you need to know the concentration. Let's just say the volume of the acid, you measured the volume, and the volume of the acid was 25 milliliter. So we know all of these information. So how can I figure out the concentration of the acid? That's when you need to come up with an known concentration of a base. So you can use sodium hydroxide base, but you need to know the concentration of that base. So let's just say the concentration of our base is, we can pick 0.5. And the volume of the base, we can figure it out by using the reading from our burette. This is what we need to use to figure out the volume of our base, that is standard, right? Standard solution. So we'll initially start with a solution that is transparent, right? But if we use an indicator, let's just say we're using phenolphthalein indicator. So if we use phenolphthalein indicator, the solution will turn pink when it reaches the endpoint. So sooner or later, you are going to see pink solution when it reaches the endpoint, right? Now, when it reaches the endpoint, obviously you're not going to have the same amount of bases that you started with. So in this case, the starting amount was 0, but let's just say we have this amount of base left, and that means the end amount is approximately 40, right? We have to measure it carefully. You can't just approximate, you have to actually take a good reading. And then 40 minus 0, that's why many people start with the initial reading of 0 so that it helps them calculate things faster. So 40 minus 0 is going to be 40. So that's the final reading from the burette, and the difference is going to be the amount that we should be using for our calculation. So take a look at what we know. We know that the concentration of the base, we know that we know the volume of the base, we know the volume of the acid. We just need to figure out the concentration of the acid. And this is when we use the formula for titration. So the formula for titration that was given in your reference table is MAVA equals MBBB. Write all of those down on your right side to keep things organized. So MA is unknown, VA is 25, then MB is, we have to look at here, MB is 0.5 and VB is 40. So that will be 0.5 and VB is 40, right? So then you replace the letters with the numbers that you have. So MA is still unknown. VA is 25. I always use parentheses to keep things organized. MB is 0.5 and VB is 40. So please pause the video and calculate the concentration of MA and then play it again to check if you have the same answer as mine. So on my right side, 40 times 0.5, that will be 20. And then on my left side, we have MA times 25. So to isolate MA, you have to divide both sides by 25. And if you do that, MA is going to be equals to 20 divided by 25, which is 0.8. And that's your concentration of the unknown acid, which is no longer unknown because we use the process of titration. We're going to practice more questions in our next video. Thank you.